Metals can be formed in three main ways: heating, cold forming, and milling. Heating makes metals malleable and soft like putty, so they can be shaped by hammering or rolling. Hot forming is used for shaping metals such as iron and steel. However, there are many alloys that would be damaged by the heat. Metals which have the ability to stretch are ductile and can be stretched or drawn when cold. Copper, aluminium, and low-carbon steels or any pure metal are ductile enough for cold forming. High-carbon steels like cast iron are hard and brittle and cannot be stretched. Milling and cutting can also be used to shape metals. Heating and hammering hot metals is called forging. Once the steel is red hot, it is soft enough to work. Hot forming is suitable for iron or steel, which are malleable and can be hammered into shape without cracking. Here, a bar is being drawn out into a longer and thinner bar. Hammering the hot metal produces a grain along the direction of stretching, in this case, along the length of the bar. This is how swords were traditionally made. This bar is going to be upset. By hammering it on the ends, the bar can be shortened and thickened. This is called upsetting. Once red hot, iron or steel can be formed into almost any shape you desire. Here, a tie rod from a car is being converted into barbecue tongs. First, it is bent, then reheated, and placed on a die and hammered into it. The flames come from the grease put in the die to allow the hot iron to be removed. This red-hot billet in the steelworks is being squeezed between rollers to make it thinner and longer. Rolling does the same job as hammering. They both compress the metal and reshape it. After a series of rollers, the red-hot billet becomes a thin metal sheet, which is stored in large rolls. To shape railway rails, an ingot is drawn out by passing it back and forth up to 5 times along a series of progressive rollers. The process produces grain direction, giving maximum strength to the head of the rail. Unlike hot forming, which uses hammering or squeezing to compress metals, cold forming works by stretching metal into shape. This is aluminium with zero temper. This means it has not been work hardened and is the most ductile form of aluminium available. This is called metal spinning, and this sheet of aluminium is going to be shaped into an industrial lampshade for a warehouse. The process must be done in small steps in order to avoid stretching the metal and causing it to rupture. The robot, using a nylon wheel, produces a matte finish with shallow grooves. In order to produce a shiny finish, this must be worked by hand. This is done by sliding a tool over the surface of the metal. These are some of the tools used for spinning metal by hand. Some slide, some roll, and others cut. This is going to be the domed end of a hot water tank and would hold water under pressure. The tool forces the metal to reform around the pattern of the spinning chuck. Spinning metal by hand is hard, repetitious, and sometimes dangerous work. So in some workplaces, robots are used to do the job. This is a CNC, or computer numerically controlled machine, and it is spinning pure copper. To teach the robot what to do, the operator goes through the sequence as it should be done. Each of his skilled movements is recorded into the robot's memory. From there on, it can repeat the actions forever. The robot doesn't mind. To curve a sheet or strip of metal, it is passed through 3 offset rollers. The setting of the rollers determines the curvature of the metal. These 2 pieces of sheet metal have been welded together and are about to go through the same process. They will eventually be part of a mixer on a concrete truck. The rollers are adjusted so that each part of the sheet becomes part of a cone. The curved metal is then tack welded sufficiently to move it out of the rollers until all the segments of the mixer are ready to be welded together. Using this process, it is possible to create large-scale sheets used in these tanks. One way to stiffen sheet metal is to put ridges in it. Here, a lid is being crimped in a crimping machine. The same process is used to stiffen roofing iron. Here, a flat sheet from a continuous roll is forced between rollers that shape it appropriately. Can you work out why there are a series of rollers? Using roll forming, sheet metal can be shaped into almost any cross-section. These are house beams. They are light but very strong, and today they often replace timber. This is a pipe being made, again pushed into shape by rollers. The edges are joined with resistant welding. Then the pipe is cut to size. Almost any process in a factory will tend to warp the sheets. Bent sheets, however, produce substandard parts. To solve this problem, this machine flattens sheets of metal by passing them through a series of rollers. These are folding machines for folding sheet metal. The fold is made by pushing the sheet metal into a groove. The skill lies in knowing how far to bend each fold. While the first fold is straightforward, after that you need to choose tools which can clear the previous folds. It is up to the operator to choose the right one for the job. Sheet metal objects are designed on CAD and CAM computers, which construct them in 3D. From this, the program can produce a plan and elevation drawing. These are used to check the prototype, and if it's okay, it goes on to the production line. The data is then transferred to a CNC machine such as this folder. Because this is a short run, all the parts will be made on the one machine. In this case, the operator needs to change the tools and feed the materials in by hand. For large-scale operations, there would be a dedicated machine to make each fold. Robots and conveyor belts would be used to feed and move the sheets along. To make holes in large sheets, another CNC machine can be used to locate the holes exactly as in the drawing. This milling bit is being used to cut slots and holes. It cannot do sharp corners. The process of cutting metal away with a toothed tool bit is known as milling.
One operation at a time.
Once again, the milling head is controlled by a CNC system that works off the original drawings.
When writing a program for this job, we've got to break it up into Cartesian coordinates, where the x-axis is along here, the y-axis is there, and the z-axis is when the tool moves in and out. Of course, we have to have some sort of an origin, and I'm assuming that that point of the job is my origin. X-axis, y-axis, and z-axis.
This milling machine is going to use 11 different tools to complete a job.
This is what they call a face cutter. It has tungsten carbide inserts, and these are retained on this particular tool with a little screw. When the tool becomes dull, you're able to turn the insert around and have a fresh edge. This tool was used to take a cut across the outside of the job. This one here is a twist drill. It's got a taper shank on the end. So this tool, rotating, fed into the job and produced that hole. The boring tool, boring the hole. This tool is what they call a spotting drill. We only use the end of the drill to drill the hole. This one here only goes down deep enough so that we can end up with a chamfer on there. The tapping size drill. This is a spiral flute tap. The flutes of the tap have a helix angle on them. The purpose of this one here is when it's tapping the hole, being a blind hole, the chips come along the flute and come out of the hole, so don't get caught between the tap and the bottom of the hole. It winds itself down. When it gets down to the right depth, it then stops the spindle and unscrews itself and comes away from the job. A smaller version of this face cutter was also used for taking a cut around the outside as we roughed the job out, roughed the outside shape out. For producing this little pocket, we used a slot drill. A slot drill is capable of drilling. So in other words, we can cut on the end of the tool. It can feed into the job and then cut around a contour. So it needed to feed in and then machine around, producing the shape. This is the tool machining around the outside, making sure that this finish here is on size and also a good finish. To machine around the outside of the job, we used a tool like this. This is an end mill. It's got 4 flutes. An end mill, you can't machine on the end of it. You can't drill a hole with that tool there. With the slot drill, we can. The end mill, we can't drill a hole. So this one here was fed in and fed around the side. Next tool produces the chamfer around the outside of the contour. And also a chamfer on the pocket. do the engraving of the letters, we used a very small tool. This tool is what they call a ball nose cutter. It's 2 millimeters in diameter and the end of it is spherical. If we look at the larger version of it, it's got a rounded end on it. It's what they call a ball nose slot drill. So it's very, very similar to an ordinary slot drill, but the end of it is completely spherical.
Knowing which tool to use and how to achieve the results comes from the metalworker's skills and experience in doing this work by hand. Being able to combine this expertise with the latest technology is helping us to create metalwork with precision only dreamed of in the past.